So welcome to everybody, okay, for this HPC workshop. And I would like first to introduce this the idea. So originally, I mean, it was intended to be a school on quantum computational material science, as you can see from the banner, okay? And because of the coronavirus situation, we had to turn it into a workshop. We didn't want to lose, we wanted to keep, I mean, the schedule on November, the same days and time, as a kind of a teaser, because the HPC school will be conducted next year, same time, okay? Even if it's 1 year in 2021, we still believed it was important to have, I mean, the HPC school as a workshop, okay? So here are the people who and the institution who supported the event. As you can see, CQT, okay, the CNRS, which is my home institution, okay, and many other institutions like A-STAR, the Nanyang Technological University Singapore, I mean, National University Singapore, the Material Research Society in Singapore, Nanyang Quantum Hub, University Côte d'Azur, Sorbonne University, and also SUTD, okay? So MajuLab is, in fact, I mean, just a few words, a joint lab between Singapore and France, okay? And I am the director, okay? I would like, before I introduce the speakers, I would like to let the floor to Marco Saita, because he's the director of the HPC school in Sorbonne University, okay? And maybe we'll tell a few words about all this idea came up to organize this school, okay? So Marco?
Yes.
Do you want to share? Do you want to share your screen or?
No. It's perfect here. No problem.
Perfect.
Just say a few words. So thank you, Christian. Welcome everybody. So we are very happy that you are here virtually. And yes, as Christian said, this was an idea that came up because we are, as you can see probably here in the red sentences indicated in Christian's screen, with my French colleagues, many of whom are also speakers today, tomorrow, and Wednesday. We have been running a yearly school, a summer school in Paris on advanced computational material science since 2015. We've done that every year, except of course 2020 because of coronavirus. And we also had a sister school a couple of years ago, almost 3 years ago, in Bengaluru in India. And so when we started to discuss with Christian about this possibility of organizing a joint school together in Singapore, because we have this structure, this MajuLab, who's a common structure between Sorbonne University, and the professor here in Sorbonne University in physics, and Singapore. So, of course, as Christian said, we couldn't do that in presence, but it will be done sooner or later. We are optimistic. It will be done like next year, possibly in the same week of November. So again, the idea today is to have young people, the young supposed participants to both schools, the Parisian one and the Singapore one, and also a bunch of other colleagues and other people around the world who are keen to see what we do in Singapore and in Sorbonne on broadly computational material science, and then what we'll try to teach next year. So the idea is that these 3 days of workshop is going to be something in between a school and a real conference, a real scientific conference with seminars. And of course, the idea is to have you all back next year for the school in presence. Thank you, Christian.
Okay. So let me just flash quickly, I mean, the program, okay? So you see there will be 3 days, okay? And this is a message for all lecturers, okay? So I'm chairing the session today. And every talk is supposed to be within a 30 minutes window. So there will be 25 minutes of talks, okay, of a talk, and then 5 minutes question. And I will tell all the lecturers, okay, when there is only 5 minutes left to their talk, so that is 20 minutes after they started. Okay, so I will stop sharing my screen. Okay, and Okay, so now I would like to introduce, the first speaker, okay, which is Guo Chu, and he will be talking about simulating quantum circuits using projected entangled pair states. So maybe Guo Chu, maybe you want to share your screen. So okay, you start. Okay, so in 20 minutes time, okay, 10 past 4, I will be telling you. Okay.
Okay, thank you.
Bye.
Thank you, Christian, and thanks the organizers of this HPC school for inviting me for this talk. My topic is simulating quantum circuits using projected entangled pair states. Here are some of the main collaborators for this work. Liu Yong and Wu Junjie from the Quanta team from National University of the Defense Technology, and Daryl Plati, my former PhD supervisor, and Huanghe Liang from USTC, University of Science and Technology of China. First, I will give you an overview of this talk. I will first talk about the classic simulation of quantum circuits is very important for near-term intermediate scale quantum computers. Also, project entangled pair states. It is a special type of two-dimensional tensor network. It is an ideal tool for simulating relatively shallow quantum circuits. And lastly, parallelization, as especially high performance quantum computing is very important for simulating such large scale quantum circuits. The outline of my talk, I will first introduce quantum circuits, and then I will show the computational task of sampling from a random quantum circuit. Then I will talk about simulating quantum circuits, why we would like to do that and how. And I will show the project entangled pair states algorithm in detail. So I will firstly briefly introduce the quantum circuits. So I will first the quantum state versus classic state. A classic state is well known to be encoded in by a single bit, 0 or 1. And the multi-qubit states, for example, a two-bit state is a bit string 0, 0, 0, 1, 1, 0. There are 4 possibilities. An n-bit classic state is a point in the discrete group with 2 to the power of n elements. So it is like in machine learning language, it is a one-hot state, 0, 0, 0 from 1, 1, 1. This discrete group. And quantum state instead, a single bit quantum state, it is a superposition of a state denoted as 0 and 1. It is a superposition. And 2-bit state, it is a superposition of 0, 0, 0, 1, 1, 0. And there are 4 possibilities. And the state can be denoted as a superposition of these states. So there are 4 coefficients. In general, a n-bit quantum state, it is a point in the high dimensional linear space, and the coefficient is a n-dimensional tensor with 2 to the power of n complex numbers. A classic state can be read out directly, so this bit string can be directly read out. But for quantum state, if we want to know information of the quantum state, we cannot directly know the superposition, which is a superposition of the computational basis or bit strings. The information can only be obtained by quantum measurement. So we measure each qubit in the basis of in the Z basis, from which we'll get 0 or 1. So the output is a classic bit string. For example, we have a state, it's a superposition like this. When perform quantum measurement, we have 0 times 8 times 0.8 times 0.8, which equals to 0.64 probability to get an outcome 0, 0, and 0.36 probability to get an outcome 1, 1. So this is how quantum measurement works. A classic gate operation and quantum gate operation. A classic gate operation, it is, for example, a NOT gate. It will, on the first bit, it will change the state 1, 0 to 0, 0. And a CNOT gate will change 1, 0 to 1, 1. So in general, a classic gate will induce a jump from one bit string to another. In comparison, a quantum gate operation, it will change all the coefficients of this vector in the in the linear, very huge linear space. For example, for this state, for this state, if we have a NOT gate on the first qubit, it will flip all the if we will flip the first qubit from 0 to 1 or 1 to 0. So it will change all the 4 coefficients of this state. And a CNOT gate, it will change 2 coefficients instead. So in general, a classic gate will induce a jump from a bit string or one hot vector in the discrete group to another, while a quantum gate operation will modify all the 2 to the power n coefficients in one go. So classic algorithm or quantum algorithm, classic algorithm is a series of gate operations. So we start from the initial state 0, 0, 0, and then we have some gate operations in between, and finally we get the solution, which is a bit string. For quantum algorithm, we have an initial stage initialization, which is also from 0. And then we have some gate operations in between, and pay special operation to this red box on the right hand side, which we can say that in between we are manipulating all the 2 to the power n coefficients for every gate operation. And lastly, there are some magic gate operations from which will reduce a huge superposition to a few superposition of bit strings with high probability, and then we measure the output and we get the correct solution with a very high probability. Here, 0.5, for example. So this is quantum algorithm. So now next I will talk about a computational task sampling from a random quantum circuit. So as I have shown, the quantum algorithm will, so each quantum gate will manipulate in all the 2 to the power n coefficients in the huge linear space. And how can we use that power to speed up our classic algorithms? For example, the prime number factoring problem, which is a very famous example. So given a number n which is known to be able to be factorized as the products of 2 prime numbers, n equals to p times q, find p and q. So it is a well-known problem, and it is used for our ISA security system. As a noise, so Shor's algorithm runs. So this figure shows that the comparison between the Shor's algorithm for factoring and the classic algorithm for factoring. Shor's algorithm grows polynomially with the system size, while the best known classic algorithm grows exponentially with system size, the number of digits in the number to be factorized. In this case, we can say that for the quantum algorithm to work, we need a huge number of qubits, because the number of qubits needs for this algorithm is from several hundreds to several thousands. So if we want to see that the quantum algorithm is faster than the classic algorithm, we need a noisy quantum computer for Shor's algorithm, which is actually not possible in very short time. So what we have now is a so-called noisy intermediate scale quantum computer. So current quantum computers are not perfect, which means that there are errors in all the operations. There are different sources of errors, like in the recent work 2019 from Google. The single qubit gate error is about 0.16%, and 2 qubit gate error is larger, and the state initialization and readout error. It seems that the state initialization and readout error is very large, but actually it is not that bad because this operation is done only for one time in the quantum algorithm, while the single qubit gate and 2 qubit gate operations are done many times. So that is really the bottleneck of the quantum algorithm. In general, the success probability is like this. It's the single qubit fidelity, 2 qubit gate fidelity times the state initialization and readout fidelity. Ideally, this assumes that these gate operations and readout operations do not affect each other, means that the errors will accumulate independently like a classic algorithm. But in real world, it is not that easy. So since we have a noisy quantum computer, there are several questions. How to characterize the success probability of such computer, because it is not guaranteed to output the correct result. And then the second is, can we find a suitable computational task for such computers? And if we go one step further, we raise the question, can we demonstrate quantum supremacy? Means that we can find a computational task which can be efficiently solved by a quantum computer, but cannot be solved by the best supercomputer in the world in reasonable time. Here comes the random quantum circuit sampling problem. It is a suitable computational task for such NISQ quantum computers. For classic problem, design a quantum algorithm to solve this problem is usually very hard, like the Shor's algorithm. It requires a lot of intelligence, and also it also requires a perfect quantum computer. But inversely, if we randomly generate a quantum circuit with only a few gate operations, and then we sample, maybe the final output is a very complicated quantum state. It is a superposition in the huge Hilbert linear space. We just do random sampling from this output quantum state. This is very easy for near-term quantum computers, but this could be very hard for classic computers. So we can find so random quantum circuit sampling is such a problem that it is easy for near-term quantum computers, but it is very hard for classic computers. So it is a suitable computational task. So what is a random quantum circuit? Here we can see that the figure on the right-hand side, it is different configurations, means different gate operations. The red line between two dots is a 2 qubit gate operation between these two qubits. So in general, random quantum circuits contains interlacing layers of single qubit and 2 qubit gate operations. And the gate, we can see that in each layer can be done in parallel. The 2 qubit gate are in general fixed. Like here on the right hand side, we use a CZ gate. We can also use other gate, for example, ISWAP gate or FSIM gate in Google's work. The single qubit gates are randomly selected. Each 2 qubit layer is a depth. We can see that these 2 qubit gates has no overlap with each other. They can be perfectly parallelized by a quantum computer. And the most important thing is that the output distribution generated by this quantum circuit, as long as the depth is large enough, cannot be efficiently reproduced by a classic computer. So now I will talk about simulating quantum circuits classically. Why and how? So why we would like to simulating quantum circuits using a classic computer? First, evaluating the success probability of a near-term quantum computer on the full circuit level. This is in comparison to, for example, randomized benchmarking, which is used for benchmark a single quantum gate operation. We would like to benchmark the success probability of the quantum circuit as a whole, because there may be crosstalk between different gate operations, and this will affect the fidelity. And second, we would like to have a classic algorithm to become a benchmarking baseline to evaluate the performance of our quantum computer. And then maybe we can use such a quantum, we can help develop and improve NISQ computers using this classic algorithm. So this is how it works. We have a random quantum circuit. We run it on a noisy quantum chip or a perfect classic simulator. And then we benchmark, we compare the fidelity between the outputs both devices. And if the fidelity is very large, we say this is okay for this algorithm, for this particular random quantum circuit sampling algorithm. And if it's not, we need to improve our quantum chip. So taking a random quantum circuit sampling task as an example, also in Google's work last year, for demonstrating quantum supremacy. So the work done by a quantum computer is very simple. It simply runs the random quantum circuit and produce a fixed number of bit strings, for example, S1, S2, like this. Or the next job are for the classic computers. So classic simulations are very important in this case. So there are two points for classic simulation. One is verification. We simulate the same random quantum circuit with a classic computer and then compute the probability of each of the bit strings, and then we can compute the cross entropy to say what is the success rate of the classic computer. And then with this success rate, we ask, can we find a classic algorithm, the best classical algorithm, which will run the same random quantum circuit with the same fidelity? And then what is the time and energy resources required by this classic supercomputer? And this is for benchmarking. So to say how much faster is our quantum computer compared to the classic computer. And this is how in Google's paper, they derived that his quantum computer is 10,000 years faster than the best supercomputer. How to simulate random quantum circuits? The mathematics is very simple. Single gate operation, it is a matrix operating on the high dimensional tensor, and 2-qubit gate operation, it is a four-dimensional tensor acting on this state. And computing an amplitude is easy. It is just to choose a single element from this high dimensional tensor. This is a graphic representation of tensor operation. Usually we use, for example, a single qubit quantum state can be represented as a vector of two elements like this. And the single qubit state, two-dimensional tensor, a 2-qubit gate, four-dimensional tensor. So single qubit operation, this corresponds to the mathematical formalism and 2-qubit gate operation. Existing algorithms. So first, this algorithm, this quantum circuit can be simulated in brute force, which is to directly store all the quantum state of 2 to the power of n complex numbers. So for example, a 36-qubit circuit requires 0.5 terabytes memory, and a 50-qubit circuit requires about 8.4 petabytes memory, which is almost the last available, the limit of the largest available supercomputer in the world. The nice thing of this method is that the time complexity is linear in the number of gates. So as long as your gate your quantum circuit is deep enough, this algorithm will be the method of choice. and tensor network states algorithm, which is the algorithm we use, and the tensor network contraction algorithm. So the difference between tensor network states and tensor network contraction is that in tensor network states algorithm, we directly store the quantum state as a tensor network states. But in tensor network contraction-based algorithm, the quantum state is not stored. There are all small tensors, and contracting them all will get the one amplitude. So a detailed comparison between tensor network states algorithm and tensor network contraction algorithm. The important fact is that the tensor network states algorithm is a general purpose algorithm, which means that it is able to simulate all the quantum operations, including quantum measurement. And there is a systematic compression for this algorithm. However, for tensor network contraction algorithms, there is only tensor contraction and no quantum state is stored. So it is not easy to simulate quantum measurement, and compression is not straightforward, cannot be done straightforwardly. So now I will talk about the project Entangled-Pair states algorithm. Why we need an efficient algorithm for verification and benchmarking? For example, in Google's work, to verify the 53-qubit Sycamore processor to adapt 14, it takes 1 million cores to run for 5 hours. So if the quantum processor keeps scaling up, for example, 60 qubits, there will be no classic algorithm to be able to simulate, to verify such large-scale quantum processors. So we really need a very high-efficient classic simulator for this quantum algorithm, for this random quantum circuits. Project Entangled-Pair states, it is a special type of two-dimensional tensor. Here is an example. For example, a 2-qubit state, which can be written 0, 0. It is a product of two separable states, and then we can write them as we can add an auxiliary index between them, which is of size 1. Then it's like that these 2 qubits are connected. So there are more types on the right-hand side. There are more types of PEPS states, project Entangled-Pair states. In general, PEPS for a square lattice can be written like this. So each tensor A will be a 5-dimensional tensor with a physics index, which is the red, which is the black one, and 4 auxiliary indices, which are the green ones. Gate operations on PEPS. Single qubit gate operation is simple. Instead of operating on all the coefficients, coefficients compared to the brute force approach, here we only need to modify a single tensor locally. And 2-qubit gate operation. For 2-qubit gate operation, we need to do some pre-processing. First, we split a 2-qubit gate operation, which is a 4-dimensional tensor, to the to the product of 2 3-dimensional tensors, which is graphically shown in the here. So it is a 4-dimensional tensor, and the result is the product of 2 3-dimensional tensors. The rank of the auxiliary indexes, index is very important. It is a reflection of the entanglement of this gate operation. For controlled gate, this rank is 2. So now, if we have already decomposed a 2-qubit gate operation into 2 3-dimensional tensors, we can do gate operations like this. It is similar to local gate operations. Now each 3-dimensional tensor only operates on a local tensor. The result is that the corresponding auxiliary index is larger by a factor of this chi. And then this procedure is followed by a compression stage by SVD. This is what is new also for tensor network space algorithm compared to the tensor network contraction algorithm. So here it is for this random quantum circuit. we can say that after every 8 steps, each pair of two qubits will be operated on by a 2-qubit gate operation. So with a depth 40, we will get a resulting tensor network with the size of the auxiliary index and most to be 32. So we can know exactly what is the size of the resulting tensor network. And then computing a single amplitude on a given basis is just to contract the physics indexes with the local state vector. And the final result is a 2-dimensional tensor with no open legs on the right-hand side. The rest thing is to contract the resulting 2-dimensional tensor network. So in figure A, for this square lattice with LH less than LV, this is a contraction path for this 2-dimensional tensor network, and we can compute the exact space complexity and time complexity. For this one, we can see that the space complexity is exponential in the shorter leg of the 2-dimensional lattice. This is a comparison to the brute force approach, for which the space complexity will be exponential in the number of qubits, which is LH times LV. And on the right-hand side, for square lattice, we found
5 minutes left.
Okay. On the right-hand side, we can see that for this square lattice, we found a special contraction path, which is even easier than the left-hand side. This is our small-scale testing. We can, on a personal laptop with we can simulate this 8x8 circuit to a depth of 25 in 1 hour. These are the large-scale implementation on Tianhe 2 supercomputer and comparison with other existing algorithms. To mention is that the work done by Summit, we simulate the same size circuit, 7 by 7 by 40. This is the largest size of the quantum circuits we simulate. In their simulations, they simulate circuits with a 0.5% fidelity. We simulated to 4 fidelity. So it is not a very fair comparison. For other work, we can see that for the same type of random quantum circuit, our simulation scale is the largest for this one. For our algorithm, we can compute that for 7 by 7 by 40 circuit, it requires 17 times 5 terabytes memory, and so this cannot be done on a single node on a supercomputer because the memory will not be enough. Parallelization has to be done. In this case, we use Cyclope C, which is a C++ package for the distributed tensor contractions. We can also use the cut technique to reduce the memory usage. It can be simply shown on the left bottom. For 2 tensors, 2 3-dimensional tensors, we can cut 1 leg so that there is a for loop outside, and the inner loop we only need to contract 2 2-dimensional tensors, which we can save some memory. So in this case, we can reduce the computation to a single node, and then a huge tensor network is cut into many smaller tensor networks, and each tensor network can be done on a single node. So in this case, the memory usage could be reduced, but the time complexity will increase. This is a cut technique used in Google's work. So some summarization of this algorithm: initialization as a pep state, single and 2-qubit operations, and measure a single amplitude. Conclusion. So here I talk about this random quantum circuit and our PEP simulation. Classic simulation of quantum circuit is very important for developing near-term noisy intermediate scale quantum computers. And PEP's algorithm is an ideal algorithm for simulating 2-dimensional quantum circuits for relatively shallow quantum circuit. And outlook. some possible improvement of the PEPS algorithm. Thank you.
Okay, thank you, Gochu. Okay, so there are a few minutes for questions. If you have any question, maybe you can just use the chat window to ask your question, or simply, address, Gochu directly. Okay, Rodolphe.
Good morning, everybody. Thank you very much for this very nice talk. I was wondering, is there some prospect of using these very nice and very powerful algorithms to represent quantum states and quantum operations on tensor networks to do on a classical computer more efficiently quantum chemistry calculations, for example, where you would map, as it has been proposed, to map to quantum computers the quantum chemistry problem into a qubit problem. In what sense can we, with this type of algorithm, also improve on the quantum chemistry results on material science on classical computers?
Oh, you mean to use this algorithm to simulate quantum chemistry problems?
Yes.
Actually, this algorithm is borrowed from computational condensed matter physics. So PEPS algorithm, it has already been a quite standard algorithm to simulate two-dimensional quantum condensed matter problems. So you see this gate operations is actually, so for this condensed matter problems or quantum chemistry problems, you have a Hamiltonian, right?
Right.
So this gate operations is like a total expansion of this Hamiltonian. So yeah, so this is the same thing.
Yes.
So I just use this technique from computational condensed matter to simulate quantum circuits.
Exactly. I had more in mind quantum chemistry, where the states of the were mapped with the fermion problem onto qubits. There you could also, because then the mapping is not through the Hamiltonian, it's really you end up with a set of quantum gates, like the variational quantum methods to that have been applied, for example, to compute the small molecules H2 with high precisions.
Yeah. So this algorithm can be used for circuit depths with a depth d, which is smaller than the number of qubits. So it is not easy. As you can see, the final task is to contracting a two-dimensional tensor network, which itself is a sharply hard problem. Even with this algorithm, you can only simulate circuits with very shallow quantum circuits. So for classic, to simulate quantum chemistry problems, so this is already, I think people have already applied this method to simulate quantum chemistry problems. Yeah, and the power is limited. You cannot simulate very large depth circuit.
Yeah, thank you.
Okay, I'd like, unfortunately, time is running fast. Okay, I'd like, there is a new message. Let me see. Okay. Okay, so let's pick up this question, but that will be the last one because otherwise we'll be too late. So there is a James Ty, okay, who is asking the question. So I will be reading, okay? So James Ty is saying, am I right to say today we are still unable to run and demonstrate the power of Shor algorithm with the quantum computer we have today?
Yeah, I think so.
Yes, so the answer is yes, right? Yeah, okay. So maybe I will, maybe you can stop sharing your screen, Gocho. Thank you very much again for the nice talk, okay? And I would like to welcome now, Pinaki Sengupta, okay, right? So Pinaki, can you share your screen? So Pinaki will be speaking about the Haldane chain with Dzyaloshinskii-Moriya interaction. So condensed matter physics, I guess, okay?
Yes, can you see my screen?
I do.
Okay.
Okay, so maybe you can start. Okay, again, in 5 minutes before the end of your talk. Okay, so 25 minutes your talk. Okay,
Okay.
I was a bit lenient with go-to because we started a bit late.
Sure.
I was a bit confused,
Sure.
but I mean, 25 minutes. So 20 minutes after you start, I will say you 5 minutes left. Okay.
Okay. Christian, one last question. Can you see my
I do.
cursor?
Yes, I do.
Okay. Thank you.
Okay. So please.
Thank you, Christian. And good afternoon, everyone. I would like to start by thanking the organizers for organizing this workshop even in these times and giving me the opportunity to share some recent results with you. I will be talking about the Haldane chain with Dzyaloshinskii-Moriya interaction. This is primarily the work of Ernest Ong, who graduated this summer and has currently joined the AI initiative in Singapore, working on artificial intelligence. Okay, here's an outline of my talk. After a very brief mention of the Haldane conjecture and our interest in integer spin Heisenberg chains, I will spend some time introducing the Haldane phase as a symmetry protected topological phase and its properties. And then I will address the question, how are these ground state properties modified when we introduce the Dzyaloshinskii-Moriya interaction? In particular, how is the symmetry protected topological character of the ground state and its behavior in magnetic field influenced by the DM interaction? And along with the ground state properties, I will also discuss the low energy excitations, the character of the low energy excitations in different ground state phases with or without DM interactions. So in 1983, Haldane introduced his eponymous conjecture, which says that integer spin Heisenberg antiferromagnetic chains have gapped ground state. That is, there is a finite energy gap to lowest energy excitations. In contrast to half-odd integer spin Heisenberg chains, which have gapless ground states. Ever since the proposal, it has attracted extensive interest from both theorists and experimentalists. As of today, there is no rigorous proof, but it has been verified by extensive numerical and approximate analytical studies. The interest in these spin chain and Haldane phases is driven both by intellectual pursuits as well as experimental reasons, because there has been several quasi one-dimensional quantum magnets that have been discovered that are experimental realizations of the Haldane phase. This gives us an opportunity to study topological state in a controllable manner by using external magnetic field, electric field, and any other external probes. However, the role of additional interactions which are normally present in real quantum magnets, most notably Dzyaloshinskii-Moriya interaction, have not been explored so far, at least in details. And this is the goal of our study. What is the Haldane phase? The spin 1 Heisenberg antiferromagnetic model is the most extensively studied integer spin quantum chain, and its ground state commonly goes by the name Haldane phase, and is the earliest and till date the best understood topological phase in interacting quantum many-body systems. The ground state is best understood in terms of the AKLT state, which states the following, that each spin 1 moment, denoted by these gray circles, is composed of 2 pseudo spin half moments coupled together and projected onto the S equals 1 subspace. So if you couple 2 spin halves, you have 1 singlet and 3 triplets. You project it to the spin 1 sector, And that is how you view each spin 1 moment. The ground state consists of these pseudo spin half moments on neighboring sites, forming a singlet on each bond. So this pseudo spin half on this side forms a singlet with pseudo spin half on this side, and so on. For periodic boundary conditions, the ground state is a product of spin half singlets on each bond. There is no long range magnetic ordering. There is a gap to lowest spin excitations, which is equal to the energy required to break these singlets. And this gap is known as the Haldane gap. The spin, if I measure the spin correlations, they decay exponentially as a characteristic of a disordered spin system. So there is no local order parameter. There is no spontaneously broken local symmetry. However, there is a non-local or topological order that characterizes this state and is measured by the string order parameter. The string order parameter can be understood qualitatively as follows. The classical ground state that I just described is each site is in a local SZ equals 0 state. Now there are quantum fluctuations to SZ equals plus or minus 1 states noted by these yellow and pink circles. Now a finite string order implies that these quantum fluctuations are not completely random, but they form an antiferromagnetic pattern between themselves with an arbitrary number of SZ equals 0 spins in intervening neighboring pairs of SZ equals plus 1 and minus 1 states. So if I were to measure the standard staggered magnetic ordering, that will vanish because there are an arbitrary number of SZ equals 0 states in between a plus 1 and minus 1 state, which can be either even number of SZ equals 0 states or odd, and that will give me a net 0 staggered order parameter. And similarly for the uniform magnetization. But the string order parameter ignores these and measures only the correlation between the fluctuation induced plus and minus 1 states. And this differentiates the Haldane state from a quantum disordered state. And now later it was shown that the Haldane phase is protected by the following symmetries. It has a dihedral symmetry, it has an inversion symmetry of outer bond center, and Kramer's degeneracy of the edge states. So it is protected by these symmetries, and that is why it's called a symmetry protected topological state. In other words, if there is a perturbation that does not break the symmetries, the ground state is not affected by this. However, our interest is in studying Dzyaloshinskii-Moriya interaction, which breaks all these protecting symmetries. But before we move on to DM interactions, let me just briefly tell you the behavior of the Haldane state in an external longitudinal magnetic field. If I apply a longitudinal magnetic field, the ground state remains unaltered at small strengths of the magnetic field. However, when the magnetic field strength exceeds the energy gap, singlet energy gap, there is a transition to a canted antiferromagnetic state, in which the spins are oriented such that the transverse components form an antiferromagnetic pattern, whereas the longitudinal components are aligned along the field direction. There is long-range magnetic ordering. Spin-spin correlation decays algebraically instead of exponentially. and there is gapless magnetic excitation. Finally, with increasing magnetic field, the canting increases. And finally, at a upper critical point, critical field, there is a transition to a fully polarized state where all the spins are aligned along the field direction. The string order identifies correctly the transition from the Haldane to canted AFM state. The Haldane state has this SPT character. The canted AFM or the ferromagnetic states do not have this SPT character. Our question is, how does DM interaction affect the phase diagram? To address that, we will study the spin 1 Heisenberg antiferromagnetic chain in a helical magnetic field. So this is the Heisenberg term. The chain direction is along the z-axis, and I apply a magnetic field in the xy plane that is perpendicular to the direction of the chain, where the field strength at each site is constant in magnitude, but the direction of the magnetic field varies from site to site in such a way that it forms a helical pattern. So phi is known as the pitch angle, which is the relative orientation between the directions of the magnetic field at two neighboring sites, and J is the site number. So this represents a helical magnetic field, which is schematically shown in this figure. Why do I study this? Because it is equivalent to a spin 1 Heisenberg chain with finite DM interaction and uniform magnetic field. In fact, we can show that under a unitary transformation defined in terms of the local spin operators given by this expression, this Hamiltonian is transferred to a Hamiltonian with Heisenberg interaction, DM interaction, and a transverse magnetic field. The reason we choose this form of the Hamiltonian is because this is better suited for bosonization studies, which our collaborators have used to complement our numerical studies. Importantly, this breaks all the protecting symmetries of the Haldane phase. So to explore the ground state phases, we start with mapping out the energy gaps of the ground state phases in the parameter space, parameter regime spanned by the pitch angle, which is the relative angle between field directions at neighboring sites, denoted by phi, and the strength of the applied magnetic field. We have used the density matrix renormalization group to study the Hamiltonian given in the previous slide. We follow two-step DMRG simulation to determine the energy gap, ground state energy gap. First, we determine the ground state, and in the next step, we determine the lowest energy state, which is orthogonal to psi 0. The energy gap is defined by the difference in energy of these two states. Now, the Haldane chain with open boundary conditions have four-fold degenerate ground state, which makes the use of DMRG extremely complicated. That's why we have to use DMRG with periodic boundary condition, although this is not an optimal situation because DMRG works better with open boundary conditions. As a result of using periodic boundary conditions, we are restricted to relatively smaller system sizes, but that gives us a robust determination of the energy gap. Now, what we find is that for pitch angles smaller than 2 pi over 3, the ground state undergoes the following transitions as a function of increasing magnetic field strength. At small b, the ground state is gapped, maintains the gap. At intermediate b, there is a transition to a gapless canted antiferromagnetic state. And finally, at an upper critical point with increasing magnetic field, there is a transition to fully polarized state. For pitch angles greater than 2 pi by 3, there is no transition to canted antiferromagnetic state. Instead, the ground state gap remains finite throughout the entire range of applied field as the state evolves towards a fully polarized phase. When I say fully polarized, I mean each spin is aligned along the local magnetic field direction, which in case of a, for example, which in the case of phi equals pi, will correspond to alternate spin pointing along the x and y directions. Okay, so now that we have determined the ground state phase diagram in terms of the energy gap, the next question we ask is, what is the topological character of the ground state phases in the different parameter regimes? Does it retain its SPT character in any of these parameter, in any part of the parameter regime? Now, right off the bat, we realize that the string order parameter is not applicable for any finite pitch angle because the helical field breaks the U1 symmetry. So we have to use, instead we use the entanglement spectrum. The entanglement spectrum are in particular double degeneracy of the eigenstates, eigenvalues of the entanglement spectrum has been widely used and is a standard measure or indicator of topological character of a ground state. What we find is that it's only true, the SPT character or topological character is preserved only for the Haldane phase that is at pitch angle phi equals 0 and magnetic field strength less than the lower critical field. So it's in this range, it is in this range that the ground state has topological character. As soon as I turn on a finite magnetic field with a non-zero pitch angle, the topological character is lost. And this is not surprising given that the helical field, or equivalently a finite Dzyaloshinskii-Moriya interaction, breaks all the protecting symmetries of the Haldane phase. So the takeaway message is that TMI suppresses the SPT character of the Haldane phase. Now, next we look at the behavior of the entanglement entropy to determine if there are any other intervening phases. Now, remember that we determined this ground state phase diagram just by probing the energy gap. Are there any other phases which we are missing by that measure? To do that, we study the entanglement entropy as a function of increasing magnetic field for 3 different values of the pitch angle: phi equals 0, phi equals pi by 2, and phi equals pi. The reason we use entanglement entropy is that entanglement entropy exhibits a non-monotonicity at the ground state phase transitions. And
Pinaki,
it's a useful probe to, yes?
5 minutes left.
Okay.
Theoretically.
Okay. Thanks, Christian. It's a useful probe to detect any hidden phase transition where the nature of the ordered phase is unknown due to the absence of any local order parameter. But what we find is that the entanglement entropy results are consistent with those obtained from the study of energy gaps. So for phi equals 0, that is along this line, there is a in the Haldane phase, the entanglement entropy is finite. It exhibits some abrupt change in the canted AFM phase and then drops to again another change at the phase boundaries. So there are no other phase boundaries. And same for phi equals pi by 2, where there are these two non-monotonicities at these two critical points. And finally, in the for phi equals pi, the entanglement entropy decreases monotonically, indicating that there is no there are no phase transitions. Okay, I will very briefly go over this before going on to the dynamics. I wanted to show the spin-spin correlation in the different phases. At B equals 0, the ground state is the Haldane phase, and the spin-spin correlation decays exponentially, which is denoted by this blue curve. For phi equals 0 and a finite magnetic field in the canted AFM phase, there is long-range antiferromagnetic ordering, which is captured by this oscillating long-range behavior of the spin-spin correlation. And finally, in the fully polarized state, the spin-spin correlation remains constant. For finite pitch angles, in addition to the long-range canted AFM correlation, there is a overlaid modulation determined by the pitch angle, and that is captured best or seen best in the fully polarized phase, which is where the spin is polarized along the local field direction. So with this, we conclude the discussion for the static properties and move on to the dynamic properties, which are captured by the characteristic, the dynamic spin structure factor. I will not go into the details. This is the expression. We calculate both the longitudinal given by the ZZ component and the transverse given by the plus minus component of S alpha beta. We use the time evolving block decimation with linear prediction to calculate the dynamic spin structure factor. Here are the results for phi equals 0. In the Haldane phase, you have this single mode, single magnon magnon mode with a gap to lowest excitation, with a gap to the ground state. In the canted antiferromagnetic state, the entire spectral weight is concentrated at k equals pi, and the excitation energy is 0. Whereas in the fully polarized phase, there is a finite gap to lowest excitations, and the magnon shows generic single particle dispersion. The behavior for both like longitudinal and transverse excitation modes are identical. But when we move on to finite pitch angle, the behavior changes dramatically. First of all, the transverse and dynamic structure factor are no longer following each other. Instead, the transverse structure factor has two branches in the canted AFM and fully polarized phases. The gap vanishes at momenta commensurate with the pitch angle, whereas the longitudinal phase always remains gapped and has a single branch. We do not completely understand the nature of these excitations. These numerics have to be supplemented by some analytic work to understand the nature of these excitations. Finally, if we keep increasing the pitch angle, the two branch nature of the transverse mode is retained, but with an extended range of intervening momenta where the two branches merge. The longitudinal mode always remains single mode. And finally, for phi equals pi, the two branches of the transverse mode merge, and once again the transverse and longitudinal modes are identical. They are always gapped. The qualitative feature remains the same, except for the fact that as we increase the field, the excitation is more localized, as evidenced by this narrow dispersion. So as I said, we need some analytic, complementary analytic work to understand the nature of these excitations, as well as the nature of the gap state for finite pitch angle, particularly for phi less than 2 pi by 3. With that, I would like to flash the conclusions, and thank you for your attention. I will take any questions you may have now.
Okay, thank you very much, Pinaki, for this nice talk. Okay, so the discussion is open for some questions. Okay, maybe I can start with one kind of stupid question. Okay, in this model where you have, I mean, a spin 1 on the chain, right?
Yeah.
The idea is to decompose to view the spin 1 as a combination of 2 spin 1/2. Okay.
Yeah.
My question is very stupid in a way. I mean, if I take for the spin 1/2, can I consider that it is made of 2 spin 1/2? Because combining 2 spin 1/2, I can get 0, 1, or 2.
Right.
I could get 1, and I could still do a project onto the 0 sector. Or should we always have, I mean, should decompose the spin 1/2 in such a way that the one is the value of the spin on each side is the maximal value that you can obtain from the decomposition?
That is correct. That is the projection to S equals 1 state.
Okay.
So if you add 2 spin halves, you get a half, or sorry, 0 or 1.
Exact.
So you project onto the 1 state, a 1 sector.
Yes.
So, and again,
then you do a singlet, right?
And then I do singlets with the pseudo spin halves on nearest neighbors.
Yes, but suppose I take 2 spin 1 on each side.
2 spin 1 on each side. So you want to
project on the spin 1 sector and on the spin 0 sector in the.
Okay, so you can project to spin 0, spin 1, spin 2.
Yes,
and you are saying that.
I'm just sticking to the 0 and 1 sector. I don't consider the 2 sector.
You know what, Christian? I think that will be applicable to spin 2 Heisenberg chain.
Yes, I understand why it would be applicable to. But why? So why isn't it applicable here?
Why isn't it applicable here? Because the local state. Oh, you're saying that local state, I can still constrain it to spin 1.
Yes, exactly.
And then what? Oh, you are saying that your constituents are. I see. Okay. One sneaky way of avoiding this question is to say that this is the AKLT state. This is not the exact ground state of the Haldane chain. This is adiabatically connected to the ground state. I do not know if you play the same game with 2 spin 1 moments, whether it will have a finite overlap with the exact ground state, or it will be orthogonal.
Mm-hmm.
So that is a roundabout way of saying I don't know. So okay. Sorry.
No, it's okay. It's okay. Okay, I have 2 questions. Okay, maybe I start with the first one who asked the question, Michele. Okay.
Yes. So regarding the dynamical structure factor, so you probe these gapless excitations in the canted AFM phase. When you switch on
very well.
When you switch on this, sorry.
Yeah, go ahead.
When you switch on the phi angle, is it clear how this evolves? I mean, the position of the gapless excitation in K, how this evolves?
That is
because I think this could be a way to understand. I mean, the second question is if you understood why there is this critical phi angle above which the gapless phase disappears.
Okay. To answer your first part of the question, yes, there is a continuous evolution of the 0 of the excitation spectrum with increasing phi.
Mm-hmm.
So here for phi equals pi by 4, these are at symmetrically pi by 4 away from k equals pi. And this is just stating the outcome of the simulations. Now, and that keeps changing with phi.
Mm.
That is what we have observed. Yes, that's true. But
okay, so when you're going towards the critical value for phi, above which the gapless phase disappears.
Mm-hmm.
I mean, why is that? Why does it disappear? And is it related to the dynamics of this gapless mode in K?
Honestly, we don't know. First of all, when we go towards the critical point, it becomes very difficult to access the canted AFM phase. We are limited to, I should have said that, we are limited to a chain length of 36, which makes it extremely sensitive to finite size effects. And that is why we have to do linear predictions to get a larger time window. All these things introduce numerical errors. So while the qualitative features are robust, I don't know how to push it towards more quantitative answers. That is why I mentioned that it would be nice to have some complementary analytical work.
Okay, last question, okay, by Tanchi Shen. Okay, his question is, how is this pitched angle phi related to the detailed DM interactions via this unitary transformation?
Yeah, Tianchi, I can share with you the details of the calculation. It's for now, I can just say, sorry, how do I go out? Yeah. I can just say that it's proportional to cosine of the pitch angle. Okay. But I can share with you the detailed calculation where you take this, apply this, and get this. You have all the components of DM in terms of the phi pitch angle and as well as b tilde.
Okay, so it doesn't matter where the detailed like that. Like this can be a very general. This can be related to a very general DM interaction. This D here, right?
Well, the DM interaction, the nature is always constrained by the symmetry of the system. So symmetry of the chain as well as the Hamiltonian.
Okay, thank you.
Okay.
Okay, I think it's time to have our break. Okay, so okay, it's a bit late, but anyway, I would propose to have a 20 minutes break.